6 inches, 7 inches, 9 inches.
Yeah, around this.
Impossible. 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 All right, let's do it again. Right, back her off.
So right now you're shooting about 80% at a 900-meter target, and you're not even trying hard.
Yeah, I'm just playing.
I know. I know. If you would spend your time at it and try hard.
That's like,
And this is in this freaking wind, by the way. You gotta
it's a decent wind, yeah.
Well, they call him Mr. Sincere, and he never sounded more sincere than he does in that song.
Should probably.
Getting pretty gross.
Ooh,
I got a clippers for you, bro. Like right now? Yeah.
I feel that. I feel the freedom coming off every pine cone, every pine needle, and every potato.
The very first thing that we did is blackout. I mean, the history of the company is in blackout. That's where PNW Arms started, and when I purchased PNW Arms some years later, the blackout was the flagship of the company. That's where we pride ourselves in the quality that we achieve with the blackout. So obviously, when we started creating specialty ammunition, it was a logical place to start. See what we can do with the blackout, because we had these ideas of we can do better than the 400-meter blackout that people were talking about. So we created this puppy here. Now the initial version of it, we demoed it at Nellis, years and years ago. It was 700 meters, and it looked a little bit different. So if I give you the original bullet and this bullet, you will be able to tell a lot of difference in how the ogive was designed, how the tip was designed. It was different. But we learned a lot from that, and then we basically go and created the 800-meter version of it. And now the difference between the 800-meter version and the 900-meter version is so subtle that I can put the two next to it and you won't be able to tell the difference. I mean, you really have to look at it under a microscope to figure out, what is the difference here. And so the way we do this is we do a whole lot of design work on the computer. So we use SolidWorks to design the bullets, and we do a lot of analysis on their flight patterns, how they behave in flight. And so we find subtle changes in on the drive band, subtle changes in the tip of the bullet make a huge difference. I mean, the difference from 800 to 900 was, a half a, I don't even know, 1/10 of a millimeter change. Basically, I changed an angle on the front of the bullet. And so we've got a couple of patent pending features on it. What's on the drive band of the bullet is a patent pending, it's already submitted, it's pending. And what's in the front of the bullet, the way we design it is, again, it's a patent pending feature, and they all designed to work together. So of course I'm reducing pressure on the front, trying to make it, well, interestingly enough, you would think that you make a small round nose, right, it'll be aerodynamic and efficient. But we find that that's not the case. And when we're making bullets with round nose, they all go all over the place. It's really hard to group them right. So then we go, okay, well, let's try a flat nose bullet, right? So that, you know, we got a tiny little flat, a maplet basically, which is of course is a side effect of manufacturing process in a jacketed bullet. So let's try that. Well, that was better, but still not quite right. So what we have now is a series of angles that make up the nose, and we find that that flies a lot more efficiently. And some of these, like the 5.56 the other day, we were grouping at 0.3 inches at 100. So really efficient. So that's the front. And now in the middle of the bullet, the drive band basically has several things in there. It's kind of complicated, but in essence it does, you know, several things. The evolution was we have a whole tray of all the bullets that they do. We just like everybody else, right? We start cutting off the drive band to reduce friction. Okay, that's where everything started. And you know, I've got bullets dating back to like 2012, 2008, when we're designing drive bands where I'm cutting out chunks of the drive band, and I'm cutting angles, right, to reduce airflow. So you can see that it comes in,
trying to streamline those corners.
Exactly. So it comes down. I never cut gas checks like, you know, in the Barnes bullet gas check, where it's a square shoulder gas check with a little chamfer. We never did that, but we had, you know, long bullets for subsonic use that had these different angles cut into it. And so it evolved from there, where we start doing you know, flow simulation on these bullets to see how I can optimize the airflow with the bullet. So that's when we come up with several ideas, where it's like, okay, well, let's put a series of them and create a wave pattern. And so basically the provisional pattern that we have on these things is a mathematical formula that describes how to create that wave pattern. Now, the reason why it's so precise and so critical on what the mathematical formula is, because it's not only reduces friction, that's only, you know, that's where our initial thinking was, but what we found out is if we create those wave patterns in a certain form, what they do is they compress the air behind the bullet, because as they fly through the air gets disturbed just a little bit through these humps as the air travels through, but in the end, when it goes to the back of the bullet, it slams down and it compresses the air behind the bullet and reduces the turbulence.
So a big part of aerodynamic drag is on the back end of the bullet, where you have a negative pressure zone kind of in that wake of that tail. And so if you can minimize that, you drastically increase the ballistic coefficient. So by manipulating the sides of the bullet, you can adjust that airflow to make it pinch down quicker and reduce that turbulent negative pressure zone.
Exactly. And so basically what we found is, based on how we modulate that formula, and based on, and it's a series of angles, radiuses, there's not a straight line in there anywhere. And it's all just a smooth flow of air through. It's basically, think about how the river flows through a bunch of rocks on the riverbed. There's no sharp angles, there's no nothing. It's basically everything is smoothed out to ease the flow of the air over the bullet.
Yeah, a basic concept that's never surprisingly been developed or employed. I think a lot of people at a glance, they just assume that it's just a small gas check, it's not going to make that big of a difference. The profile in a gross sense on that scale doesn't appear to be that different. And so that's something we're talking about earlier too that's very interesting, is back in the day before we had SolidWorks software and you could put this into a supercomputer and figure it out. I mean, a modern computer being a supercomputer by old standards, right? And adjusting all these different parameters, you know, digitally to see what's going to happen. The software is getting so good now where you can actually simulate that fluid flow pretty effectively. And in the old days, they'd have to actually create the deal,
do the spark photography.
The photography. They'd have to do empirical testing, which is like a huge amount of work. and time and investment, money, just for one possible deal. And so they eventually land on something that works better, and when they run out of cash and time and blood, sweat, and tears, then they quit.
Yeah.
And so you're picking up where people left off with the old school way of development of these technologies by using the software and being persistent.
It's pretty addictive.
I bet.
Because you're sitting in front of a blank canvas, and I've got, so people look at it and go, oh, it's a hybrid. Or no, there are mathematical formulas everywhere, and I'm using mathematical formulas that basically set up relationship on these different parts of the bullet. So this is not, and every bullet is 3 circles, right? Mm-hmm. And out of 3 circles, you got a bullet designed. Well, but the question is, what circles are you going to use? And so in terms of hybrid OJAV, they always talk about, oh, this and that, this based on the diameter. I'm not using any of those. These are formulas that I set up specifically that's in relation to the groove, the depth of the rifling, and the diameter of the bullet, and they very precisely define my thinking on how the transition between the 3 circles that form the ogive
Right.
basically will be set up.
Yeah, when you're talking about the dynamics of how air flows over a projectile that's going supersonic, it's like fluid dynamics, right?
Yep.
And any tiny little difference is going to make a huge difference when you're talking about long-range shooting and ballistic efficiency, right?
Yep.
And so just the tweaking that and we're looking at some of your inspection instrumentation back there that you guys use, some of the optical inspection stuff where you can speed up the process of verifying that everything's to the proper spec, because it's so important to have those angles exactly perfect. And if you tweak it just like half a degree in the wrong direction on a tiny little surface or corner, it might completely disturb that flow.
And absolutely right. And you can have a bullet that look just like the other one, and you won't even notice it. But in a simulation, I can show you that the way it disturbs the air and the way it flows, it does not compress the turbulent air behind the bullet as much as the other one. And so tiny little changes have huge effect. I mean, that's how we went from 7 to 8 to 900 meters with these rounds, is to make very subtle incremental changes that have a lot of
huge real world effect,
a lot of science behind it.
And after verifying it through your empirical testing that you do at your shooting laboratory and stuff like that, what a guy finds out is that those subtle changes, although the bullet may appear to look very similar, in practice, it completely changes the ballistic coefficient profile. And even the drag model's like not really appropriate to map how it's going to perform in this trajectory. Because, I mean, you can modify some of those things and you can band those BCs to kind of simulate or duplicate that. But if you just plug in the dimensions for the bullet and stuff into standard drag models, it's going to come out a little weird.
Right.
And so maybe that's why people who take a glance at these things without paying enough attention to details don't understand that it's those details that make the G1 and the G7 not really the proper deal. They might have to even make a completely new drag model to model that trajectory.
Right. Basically, that's exactly what we're finding. The empirical data gives me, the speed information at the muzzle, and we know what our drop is at certain distances. So we know all of that. And then we're trying to fit it into the I didn't even try the G1 because that's just ridiculous. It's never going to work. But we tried the G7, and the G7 I can map. My choice is either map it to the front of the trajectory or the back of the trajectory, because I have not yet been able to. I can get pretty precise drop tables out to about 70% of the trajectory, but once it changes it goes from supersonic to subsonic, right past that area, I'm having a problem trying to map what the bullet does to
because the other bullets,
the drag bullets, because they behave differently.
Completely differently, and that's kind of one of the critical zones too. And we talk about the transonic stability problems that most conventional projectiles have, is the destabilization in that transonic zone. And really achieving dynamic stability through that is something that you have worked on for a long time. And some of these cartridges are honestly, in my opinion, kind of maybe ahead of their time, and so, like the projectiles even, because, and that's one of the interesting things about you guys, is you develop stuff that you're trying to perfect the science and see how far it can go, even though you might not necessarily be able to market it right off the bat until it catches on. But it's just a really cool science project to see this like what's possible just by adjusting the subtleties.
I mean, and you take the 300 Blackout for example. I mean, you ask anybody, they say 300 Blackout. It's a 400 to 500 meter round. Okay, I had this. You know, I was just at a shoot at Vegas at SHOT Show for SOCOM. You know, special ops across the world. One of those invitation only events. I met so many people that call BS on this round. It's not even funny. Everybody says it's not possible. 400 to 500 meter, maybe. 900, no way.
Sure.
And so we got them to sit down and shoot it. And I think all it is just perceiving ballistics differently.
Sure, people are thinking kind of inside.
Physics.
Yeah, they're thinking inside the old box,
Yeah, exactly.
which is with other drag models and other proportions of conventional bolt design, that would be kind of an impossible deal.
Yeah.
But if you can repair some of the drag issues on the tail of the bullet and drastically change the BC, another interesting thing too, and we talked about this, we hinted at it a little bit, is because you can drastically improve the BC subtly with these subtle changes in the geometry, you can change the material to something a little lighter than lead, and you can still make it stubby and short to increase your gyroscopic stability, because your center of gravity and pressure are closer together.
Yep.
So the bullet's more inherently stable gyroscopically, but it's still a high BC.
Yeah, but and then just look, take this round for example. Okay, I don't have a 6.5, so excuse me. I'm not a great believer of the 6.5, but take the 308 round. Okay, so basically people take the 308 and hey, we made 6.5. Look at it. We shifted the ballistics by 200 meters. Great. Well, okay. So you're telling me that you made a bullet skinnier and longer,
which is under conventional thought inside the box of the current geometry, the only way you can increase the ballistic coefficient, but then you sacrifice your stability because you got a longer, skinnier bullet, which requires more twist to even kind of get stable.
And so guess what happens? You get into that transonic region, center of pressure, center of gravity.
It exacerbates your transonic destabilization.
And you basically will destabilize faster. So yes, you improved the round. I'm not saying that you didn't. You got an extra 200 meters on it. Well, I went with it in a different direction. And this is a science project because based on what we were able to achieve with the Blackout, we said, okay, I like the science behind how that works. Let's go and add the science to other rounds. So take the 308, we made a 375. Now what I did, there's nothing by accident on that bullet. The length is very precisely controlled. I designed the bullet before I designed the case for it. Because there's a very specific relationship between the length and every other feature on that bullet. And what I'm trying to do is make the shortest, fattest bullet that has the highest BC that I can squeeze into that cartridge.
So you're maximizing both your stability and your BC at the same time, so you get the best of both worlds.
Exactly. So I'm designing the ogive based on a whole set of parameters that's very deterministic. It's not by accident. I'm not just going around and sketching things.
So is it just giving me a bit more?
Yeah, this one is 5 mils. This one.
Oh, it's at 5. Charles, your bullets are too pointy. They're poking me. Ooh. Ready?
Yep, signed up.
Okay.
I can't hear nothing, I can see nothing. It's killing me. Oh, now you got 3 holes in the middle of the plate.
Oh, really?
Okay, so
Are you serious? All right, man. I'll send another one.
And they are like 4 inches apart.
Alrighty, I got one more.
All right, send it. Oh man, yes, that's top of the plate.
Back it up.
Less than 10 inches above.
Oh yeah. So we're at 1,300 meters.
Meters, not yards.
And the last few were about where? Kind of.
You had 3 of them like that, literally, like 1, 2, 3. They have one here and then one there.
Yeah, that was when I was trying to hold over because I thought it was cool, and I was wrong.
I can pick up a bullet for you. Very soft.
Are you ready?
Oh, I'm sorry.
So here we are at the 1,300 meters with the 375 TROM, and we got 3 right there, and they actually got some, and one up here. That's when I tried to get smarter. Then
that was the very first shot. That's when you were trying to get it on target.
Yep. And we got some pretty good deformation of the steel here, but once we settled in on the firing solution, it groups them in there pretty darn good, man. I don't know how far that'd be, but
It's probably 6 inches.
yeah, 6 inches, 7 inches, 9 inches.
Yeah, around there somewhere.
Yeah.
You ready to move the razor?
Nope. We're good. So we went and inspected the target at 1,300 meters. Now we're about, I don't know, 1,200 meters downrange looking at the target here. We're going to direct some fire from down in this little valley. And what we're going to be listening for is the sound of the bullet passing over our head. You can tell a lot from that. If it's got some radical yaw or a tumble going on, you'll hear that. If it's flying nice and slippery over our heads, you'll be able to tell the difference. So it's kind of an informal way to qualify how stable the bullet is in flight. You boys ready?
Ready when you are.
Roger, roger. Send a few.
What was that, Charlie?
Gun is hot.
All right, send it when ready.
Whoa, that was... I didn't hardly hear anything, yeah.
Beautiful. I wasn't looking for a signature. Send another one.
Okay, coming your way.
One, I didn't see it. Beautiful, solid hit on the plate, guys. Keep another. Send another one.
It's a slippery one.
And what we're able to achieve with the 375 is I'm trekking through the transonic region with undisturbed. And instead of pushing the same curves of a 308, now I'm just not 200 feet up. I'm completely changing the curve. I mean, when you start out of the muzzle, I'm slower than the 308 by about 400 feet per second. Interestingly enough, funny you should mention, at 400 meters, I'm faster than the 308 bullet because I'm decaying energy less than the 308.
Yeah, because the BC, if a guy had, and that's another interesting point too, is people are demanding to have some kind of BC value so they can generally categorize it. But the thing is that those BCs are based on drag models that are not suitable for these projectiles. So it's kind of hard to give a definitive answer on what the BC value is.
And
we can give approximations.
And I think BC is old-fashioned. That's in the past. What we need to move to is, the same things that like the Brian Litz guy's doing, the applied ballistics, 4 degree of freedom simulators, and custom drag profiles for the bullets. And then I can tell you exactly what the bullet is doing.
Yep.
Well, I'm working on it, not ready yet, we'll get there. But the whole point is that when I go to the 375, I'm not only trekking through the transonic region, I'll start warming up my bullet at 1300 meters. And at basically at 1800 meters is where I'm dropping below the 300 foot-pound magic limit for what the military says that's a kill shot. And so I'm putting my effective range out to 800 and plus, because at 800 I'm still tracking straight. I have plenty of energy in the bullet left. And so basically what we have is we're tracking all the way out to 800 going straight undisturbed through the transonic region because the stability of the bullet and how it's designed. Now at those distances you got quite a bit of elevation. And so I totally understand that back 20 years ago you would have solved the problem of you don't have enough elevation in your scope by making a faster, skinnier bullet with a flat trajectory. But nowadays with all the new technology that you've been reviewing on your show and all, we have a solution for squeezing.
There's ways to get more elevation out of the deal. And if the bullet's performing consistently, even at those extreme ranges, because you've defeated that transonic barrier, it's really just an issue of dialing that optic into the right spot.
I mean, here's how I think about it. So, you basically, and no matter which bullet you take, you will have enough to go out to 1,000 meters, right? So what you do is you set your zero your scope with your bullet at 100, and you click it up to get to 1,000. When you get to 1,000, you will not have enough in your scope to get past 1,000 with this. I'll put one of those
Charlie Tarak or
one of those things in front of it, flip it down, crank your turret all the way back to zero. So now your zero is at 1,000. So when you want to go to 1,100, well, what's the difference.
In the last few years, there's been some real good advancements in gaining elevation adjustment out of a rifle. So that issue is now resolved.
Exactly. So, ballistically, basically going this way where you have a stubbier, more stable bullet that tracks through the transonic region and ignores the transonic region makes a hell of a lot more sense when you've got. I mean, look
it's
at
a prioritization of characteristics.
I mean, look at anywhere in the trajectory. Like even if most ranges, let's like between now and 1,000, I have almost an extra 50-60% of kinetic energy in this bullet than the 6.5.
Yeah, and a lot of these things, are really defined by what our parameters are for exactly what we're trying to accomplish. But when you're talking about getting the most range out of a particular magazine style, like you can run this 375 in an AR-10 platform, and you can get 2,000 meters out of it because you don't have to worry about the transonics. You still have energy, terminal energy on target. You have a little bit more elevation to worry about. But so it's really a prioritization of those characteristics that you need to accomplish your particular mission. Now, some guys might require a flatter trajectory if they don't have the ability to range a target as accurately or the ability to precisely adjust for it. It's a little more forgiving. The danger space is a little easier to deal with, on a flatter shooting round. But for guys that are dialing it in with precision, who are, precision long-range shooters and need a little bit more energy on target in an efficient way, this is a very interesting way to skin that cat. And you're bypassing a lot of those problems that have, like you said before, the limitations of the max effective range of cartridges inside the supersonic realm has really pushed the technology to be faster and try to maximize that supersonic range. And so just by bypassing that issue, now it unlocks all these other options that before were rendered obsolete.
The interesting thing is that the more I do this, the better this equation gets, because with the blackout, when you go from 5.56 to the blackout, but you lose quite a bit of case capacity. When you go from the 308 to the 375, I'm losing less case capacity. When I go from the Norma Magnum to the 475, I'm losing even less. And by the time I get to the 50 cal, I mean the 50 cal bullet that I'm working on, it's over 1,000 grains, and I'm losing only probably 12% of the case capacity out of the 50 cal. And so I'm getting incredible amount of kinetic energy out of something like a 50 cal because the bullets just get ridiculously heavy. But I mean the same concept stands. I'm trying to make a very aerodynamic, stubby little bullet that is very stable.
So the advantages here are, just to simplify it, is increasing stability and ballistic coefficient at the same time.
Yep.
Because otherwise it's a trade-off. And
Yeah,
so by
exactly.
bypassing those issues and maximizing your efficiency with the subtle flow dynamic improvements on the gas checks of the bullet and all the geometry on everything in it, you can get away with a lot of other stuff that other outfits wouldn't be able to get away with.
Well, and you know, the other thing is we have, I mean, you're saying the tip of the iceberg here, because right now these bullets are manufactured using, you know, a Swiss screw machine.
Mm-hmm.
It's time consuming. I mean, those guns, it's great, lights out operation, it makes a lot of rounds, whatever, great. But it's not as fast as I would like it. So we have, you know, pet projects in the background that we're working on injection molding these. And so, well, it's not quite injection molding, basically going in and creating them. You can think about it like metal injection molding.
Mm-hmm.
But we got the process perfected. We got some prototypes where we getting like 5 microns of accuracy on the features. So we actually pushing this technology to a point where, in a not so distant future, I can create these in a lot more efficient way. And in addition to the geometry, I can control its terminal performance.
Mm-hmm.
Because once I get to this metal injection molding type construction for the bullet, I can control how it disintegrates on target, where it stays intact and behaves like an FMG, or whether it goes and disintegrates like a hunting bullet, or whether it you know, it can have multiple different types of properties and behaviors. It can make it, you know, a shorter range training round, a lot cheaper cost, etc., etc. So there's a lot of things in the pipeline that we're working on, and it's
That's
all
one of the
just,
interesting things with
feature stuff.
with what you guys are doing too, is just creating your own tooling, advancements in the ammunition manufacturing process to get more consistent results with, you know, more speed and efficiency in manufacturing is going to be pretty cool for the industry as well. So
The one thing that we're very heavily focusing on is material science. I mean, these are made out of brass, okay? Anybody can make bullets out of brass, great. We proved the concept of, it's all about the geometry and the density. So we proved the fact that, you know, this concept is solid. I can scale it across calibers. We have several versions of it available right now on the website. Where we're going with it is, in terms of material science, we figured out how to create variable densities. So basically, we figured out how to create a blend, a material blend that we can injection mold and create bullets and vary the density. Now what that will allow me to do is, instead of the 245 grain bullet that's in here, I can easily push this out to be heavier than a jacketed lead equivalent. So now I'm at a point where I can shoot, instead of you know, the 308 175, that's the long range, you know, basically gold mark right now. Instead of 245, I can start shooting much heavier bullets. And
so
I
without
can
adjusting the external geometry,
Nothing
you can
changes.
just change the material,
Just like,
and
yeah,
you adjust the
exactly.
physics that way.
Exactly. And what it allows me to do is, it allows me to make it even stubbier. So instead of you know, having the next at a certain point in the inside, I can start making it shorter
And maintain that ballistic coefficient and increase the stability.
Yes.
That's
So-
brilliant, man.
So we're working on that. Those are all future projects. It will take some time to get to, but we got a lot of. We're working on a hunting variant of that, where we basically combining all the science that we mentioned and kind of alluded to, create features on that bullet that just have devastating effects. And I might share that video with you so you can show it to the guys to see what it does. Stupid thing killed my workbench. You know,
Yeah,
it's killed my.
Incredible terminal performance.
So we'll talk about that. But I mean, those are all future things, so this is not the end of the road. Basically, this is where we're starting, and I believe that we're on the right path of where ballistics should go. And I think the fundamental thing is, question everything and don't believe nothing.
but she hits me, disassembles my leg. So I went to the doctor and he gave me a leg. Now she waits, this number